Greetings and welcome. My name is Mr. Waddy, and I'm just doing a quick review for my pre-calc students. We are currently looking at trigonometric identities and equations, and this is found on A62 in our book. And this first example, we are given a ratio for one of our trig identities, here's sine. We're told what angles theta is restricted to, so between pi and 3 pi over 2, that would be in the third quadrant. And we are also looking for secant of theta. So if I know sine and I'm looking for secant, I'm going to have to build a relationship between those using our trigonometric identities. And we don't currently have one that directly relates those two things. However, once I know sine, I can find cosine using this Pythagorean identity. And once I know cosine, I can find secant, because secant theta is the reciprocal of cosine theta. So using a combination of these two separate identities, we'll be able to kind of stepping stone our way to a link from sine to secant. So the first thing I'm going to do is plug in what I know into this equation for sine. So I have negative 4/5 squared plus cosine squared theta equals 1. So if I square this, that's 16/25 plus cos squared theta equals 1. Subtract 16/5 from both sides, or sorry, 16/25. And this I'd have to multiply by 25 over 25 to get a common denominator. 25 minus 16 is going to be 9, so cosine squared theta is going to equal 9/25. And to get cos theta by itself, I've got to root both sides, plus or minus. Don't forget it. Now, I still have one fact that I can pull from, though, because I actually want to restrict it to one of these signs specifically. And in terms of our quadrants, sine theta we know is positive in the first and second quadrant, and cosine theta, and its counterpart secant for that matter, will be positive in the first and fourth quadrant. So since we're in the third quadrant from this angle restriction, I'm going to specifically choose just the negative value here because of that angle restriction. So cosine of theta is going to equal the negative. Square root of 9 is 3, and square root of 25 is 5. So here's cosine of theta. Still not what we were looking for, however. We were interested in finding secant. So now using substitution, I can find secant by plugging cosine in there. And actually, in this case, I could just quickly reciprocate it if I wanted, but I'll do some proper math out to justify that. So negative 3/5. So I've got kind of a stack of frac situation. So the way I can deal with that is multiplying the numerator by the reciprocal of the denominator. So that's negative 5/3. And so I get secant theta equals negative 5/3. Right? So there's one of the first uses we had for trigonometric identities, using them to move from one ratio that I know to one that I don't know. And the more complicated ones were like 2 degrees of separation, where I had to use multiple identities to get my result. And some of these questions were a little bit more open-ended, where we didn't necessarily have to all use the same strategy to get that result. Let's see. Another kind of problem that we had was verifying trig identities. Let me just get a snapshot from the book. I think number 8 seems interesting. Oftentimes in this case, it was actually our fraction work that was more difficult for us than anything, whereas we were somewhat experienced with the trig identities themselves. Let's see, let me just open up this. Okay, good. So for this problem, I'm asked to verify, meaning I want to show that the left-hand side is equal to the right-hand side, and I want to show that any way possible. Now in this case, I've got, I've got a whole bunch of fractions going around here, and I have an equation. So one of the ways I'll often deal with this is multiplying both sides by the LCD in order to kill the fractions. But the first thing I realize I can do is cotan x I could rewrite as cos x over sinx, since that would write it with another fraction with a common denominator. I do see this secant x up here that I might have to deal with. Yeah, I think I'm going to deal with that from the beginning. I could technically save some of this for later. So secant of x is going to be 1 over cos x. So using these two trig identities, I'm going to substitute their counterparts. And this is a common tactic for these types of problems, is rewriting the expressions all in terms of sine or cosine. It's not always going to be helpful, but in this case I think it might be a little bit. And then I can do some fraction work over here. This is a stack of frac again, so I could multiply the numerator by the reciprocal of the denominator, and I would end up with 1 over sinx cosx minus sinx cosx equals cosx over sinx. And now it's a matter of fraction work that's going to come into play. So the first thing I'm going to do is try to figure out what the LCD is of all of these denominators. And it appears as though it will just be sinx cosx, because each of the denominators could be reduced or canceled by this LCD. And the tactic I'll use, I'm not actually looking to find common denominators in order to add or subtract these fractions. I'm interested in just killing the fractions outright, and I'll do that by multiplying both sides by my LCD. Let's see, I think I have enough room there. Good. So when I multiply this, I'm going to have to distribute this to each of these terms here. So when I multiply this, the LCD will actually fully cancel out with this first term, leaving just 1 for that. When I multiply the LCD by the second term, the cosx's will cancel out, and I'll be left with the sine x times a negative sine x, so that's minus sine squared x. And here, the sinx will cancel out with a sinx, and I'll have cosx times cosx, or cos squared x. And now I've got a variety of options. I think most people will realize that I've got some squared trig functions, and these ones all happen to relate using this particular Pythagorean identity. So I could arrange that any way I'd like. I think I'll use this tactic of adding sine squared to both sides, and I'll end up with 1 equals sine squared plus cos squared. According to this is 1. So 1 equals 1 is a true statement, so this problem is verified. Verification often uses some type of substitution of one, of the trig identities or another. Sometimes it requires some fraction work or just some algebraic manipulation. But our goal at the end is to have one expression equal to another. It doesn't necessarily have to be numerical. I could have actually in this case had cos squared x equals cos squared x, or whatever else. But that's my objective in a verification problem. Let's see, I think I want to try one more problem. Let me grab one, snapshot it. Looks like a good one would be sum or difference identities. Yeah, I think I'll grab one of these. Let's see. What's funny is this one's going to be a test. Oh, I just undid. No, good. Alright, paste. Here we go. So, so the objective for this problem is to use sum or difference identities to find the exact value of each trig function. So the goal is find the exact exact trig value. So in this case, let's see, sine of 255 degrees. I often like to draw a picture just to see where we are. So sine of 255 degrees is somewhere about right there in the third quadrant. So the first thing we can do is, I like to write it in terms of a reference angle. So the reference angle is the angle measured from the terminal side of the angle to the nearest x-axis. In this case, it's the negative x-axis. So I could find this by doing 255 minus 180. So what's that going to be? Is that yeah, 75 degrees, right? Is the value of the reference angle. The other thing I have to take into account is that this is the third quadrant, and when I rewrite sine, this as the sine of a 75 degree angle, I have to take into account that sine is positive in the first and second quadrant, but it's negative in the third quadrant. So this is the same as the negative sine of 75 degrees. So I still have to deal with the fact that I don't know what sine of 75 degrees is. However, I should be able to use one of our sum of difference identities. So if I can rewrite 75 as two angles that I do know, it looks like I could use actually a couple options. I could do 75 is equal to 45 plus 30, which is probably the one the book's anticipating we'd use. But I think I also could do 75 is equal to 90 minus 15. But then I'd have to do some additional work to find 15, which is possible, but it'd be a 45 minus 30. So I think this is the best choice that we'd use. So this is equal to negative sine of 45, or I'll write it from smallest to largest, 30 plus 45 degrees. Now, the sum identity for sine is as follows. Sine of alpha plus beta is going to equal sin alpha cos beta. Let's see, hopefully I don't run out of room for you here. I'll write it underneath. And if this is a plus sign, then this is a plus sign for sine. And then cos alpha sine beta. So that's what I'm going to do here, where alpha will be the 30 and beta will be the 45. And I might, I'll likely deal with this minus sign all the way at the end. And let's see, I'm going to continue with this down here. So let's see, minus, or the opposite of, let's see, that would be sine 30, cosine 45, plus cosine of 30 sine of 45. And I'm able to determine the exact trig values. Sine of 30, I'm actually going to use my little hand trick here, is a half. Cosine of 45 is rad 2 over 2. Cosine 30 is going to be, let's see, root 3 over 2. And sine of 45 is rad 2 over 2. So that's the opposite of. Let's scroll down. And let's see, so this is rad 2 over 4 plus rad 6 over 4. So that will equal negative of rad 2. Let's see, actually we want to make the negative outside the fraction. Rad 2 plus rad 6 all over 4. And that should be the value of this sine of 255 degrees exactly. So it's negative because it's in this third quadrant, and then I was able to use the sum identity in order to evaluate it based on angles that are kind of primary angles, if you will. Alright, so let's see, I guess if you're interested in still watching, maybe I'll do one more example from solving. I thought I saw a good one in here earlier. Let's see, sorry, just moving stuff around here. Difficult to actually get the camera lined up with the one I want here. My apologies. There we are. So I'm looking at question 19 on the same page. Let's see. All right, paste, and here we are. So now our objective is not to verify this, but our goal is to solve the equation. In this case, the directions indicate that we're looking for the principal values of x. So if it ends up being cosine, I believe we'd be interested in the first and second quadrant. If it's sine, I'd be interested in the fourth and first quadrant. So looking at this expression, my first goal would be to rewrite all of this in terms of a single type of trig identity, if possible. And sine x, I can't really rewrite in terms of cosine, but cosine squared, I believe I can use modified Pythag. I think 1 minus sin squared x is be able to substitute for that. So that will be my first move. So 2 times 1 minus sine squared x plus 3 sine x. And actually, I'm going to move this 3 to the other side here, subtract 3 from both sides, set it equal to 0. I'm anticipating that I'll have to factor this problem in order to solve it. So having it set equal to 0 will allow me to use the zero product property. So let's see. So we'll distribute. So we'll have 2 minus 2 sine squared x plus 3 sinks minus 3 equals 0. And then I'm going to just combine some like terms here. 2 and negative 3 will combine to be negative 1, right? And I don't actually like having my first term be negative when I write this in standard form, so I might actually change all of the signs here. So I'm going to write this as positive 2 sine squared x minus 3 sine x. And then these combine to be negative 1, but since I'm changing the signs, it'll be positive 1 equals 0. Now, I still can't solve one of these individually. I can't combine them. However, this expression is factorable. And one of the ways we're going to do this is using U-substitution, or we're going to factor using quadratic techniques. So I have to think of 2 times what squared minus 3 times what plus 1 would equal 0. So I have to determine what would go in these parentheses, and what would work is sine x in both cases. So I'm going to define my variable u. Actually, let me use blue here. U is equal to sine x. So I'm going to rewrite this as 2u squared minus 3u plus 1 equals 0. And now this is an expression, since it's written in terms of the variable u, I can factor this, and in this case I'd have to use the AC method, which you might not recall, but the way I do this is I multiply a, the coefficient of my quadratic term, times my constant, and I get 2, and now I'm interested in finding the factors of 2 that add to my b term. And in fact, 1 and 2 do that. So now I split the b term into 2 like terms. So I'll have a u and a u, plus u still tagging along. And the coefficients of these terms are going to be the factors that we just found. So I'm going to have a 1 and a 2. And it doesn't matter which order I write it. Some people would want to put the 2 first because they'll realize that these guys will do buddies in the next step. And I still have to determine the signs of these terms. Now they multiply to be a positive 2, so their signs must be the same, yet they add to be a negative, so their signs must both be negative. And notice, in fact, negative 2u and negative 1u would combine to be negative 3u. So the next step is called factor by grouping. And this is all part of the AC method, which actually I do believe I have a video on my YouTube channel for my Math 3 class covering how the AC method works, if you needed a quick review. So what I do now is I factor out the GCF from just the first two terms, which looks like that would be 2u, and the GCF from the last two terms, which is 1, but better yet, I'm going to factor out a negative 1 because I don't want to leave my first term in my set of parentheses as a negative, if that can be avoided. So 2u times what minus 1 times what equals 0. So moving right along, 2u times u is 2u squared, and 2u times negative 1 would be negative 2u. And now similarly, negative 1 times u is negative u, and negative 1 times negative 1 is positive 1. And in order for this next step to work, these two sets of parentheses must match, and they do. So what I'm able to do is really think outside the box, where I actually steal these entire expressions and yoink yoink those out front. So I'll have u minus 1 times 2u minus 1 equals 0. And now that I've got this factored, it's set equal to 0. One of these equations has to equal 0. So either u minus 1 equals 0 or 2u minus 1 equals 0. And I solve these, I get u equals 1 or u equals 1/2. However, if you remember all the way back to the beginning of this problem, we weren't interested in originally solving for u, we were interested in solving for x. So the way I can do that is plug, well, hey, sine x is equal to u, so I can plug this back in for u in both cases and solve. So I will have sine x equals 1 and sine x equals 1/2. And I'm interested in when are these expressions true. So to solve this, the way you get rid of the sine is with a sine inverse. So I sine inverse both sides, and similarly over here, it's inverse both sides. And I get x equals, sine inverse of 1 is asking the question, for which angle will sine have a ratio of 1? And that occurs at 90 degrees. And over here, for which angle does sine have a ratio of 1/2? And that occurs at 30 degrees. And those would be my principal solutions. There are technically these also could have occurred in the second quadrant for sine if I had a greater possible domain or possible values of x. So that's kind of the most complicated type of problem when solving for a trigonometric equation. Sometimes factoring can come into play, but typically your goal will be to write it in terms of a single trigonometric identity. In this case, we had to factor and solve, and then often we end up having to use inverses to get our answers isolated. So, thanks guys for watching my review. Hopefully you'll be ready for your test coming up, and I'll try to put in the comments each of the problems that I went over, so that way you don't have to watch the whole video to figure out which ones I did. Alright, thanks so much. See you guys later.